So today we move on to problem number 2 of the series on the almost impossible integrals, sums, and series. And our problem today is the expression shown here, I of m and n being equal to the definite integral from x equals to 0 to x equals to 1 of x to the power m times natural logarithm of x to the power n. So let's see how we may be able to solve this. This is an interesting problem. So what we'll do is we'll begin with the solution, then we'll move forward to show how to solve it. Problem, the definite integral from x equals to 0 to x equals to 1 of x to the power m times logarithm or natural logarithm of x to the power n is essentially equal to negative 1 to the power n times n factorial over n plus 1. So this is the solution, and we're going to begin from here and then move forward to show how the answer is as follows, or as shown there. So our problem here can be expressed as the derivative of x to the power m plus 1 over m plus 1 times, and from here we're going to use integration by parts. What does integration by parts say is that when you have an integral where you have the integrand as the product of function v and the derivative of function u, then the answer is uv minus the integral of the product of a function u and the derivative of function v. So with that in mind, this part here is our v, and this part here, this part here is, this is our u, and this part here is our v. So our integral becomes, uv becomes x m to the power m plus 1 over m plus 1 times natural logarithm to the x minus, we can pull the constant out, and then our u, which is plus 1 times the derivative of natural logarithm of to the n dx. The derivative of that is the same as n log n minus to the 1 times the derivative of log, and this here is 1 over x, so this is the same as n over x log n. That is that. Okay, so let's just box that for now. And since our problem was since this was our problem, we can see here that this is 1 over m plus 1 as x, or limit as x tends to 1, x to the m plus 1 log to the n x minus limit as x tends to 0, x. Now you see that this part here goes to 0, log of 1 is 0, x to the power n plus 1 as x tends to 0, so this part also goes to 0. And then minus 1 over m, 0, 1, x to the power m plus 1, and we found this derivative to be n over x log n minus 1 x. So since this part is 0, this entire part goes 0, our integral becomes n over, sorry, this is m plus 1 over m plus 1 times integral from x equals 0 to 1. This goes and this one goes, so we have xm log of to the n minus 1 x. Okay, so our integral 0 to 1 xm log to the nx, it has become that. So in the expression we began with I of mn is equals to n over m plus 1 I of m n minus 1, such that I of m n over I of m n minus 1 is equals to n m plus 1. Okay, so this is interesting. So we have now said that our problem Im of Imn over Im n minus 1 is equal to negative n over n plus 1. And generally we can express this as Imk over Imk minus 1 being equal to negative k over m plus 1. So what does that mean? It means that if our Imn is equals to Imn over Imn minus 1 times Imn minus 1 over Imn minus 2 all the way up to Im of 2 over Im of 1 times Im of 1 over Im of 0 times Im of 0. Since these guys cancel, you know, there's a 2 here and that cancels, and there's this and that eventually cancels, so we remain with this. So if that is our scenario, then that means that our problem up to Im 2 over Im 1 times Im of 1, 0 times Im of 0 means that this is the same as negative n m plus 1 times negative n minus 1 over m plus 1 times negative n minus 2 over n plus 1 all the way up to this point where we have negative 1, 1 over m plus 1 times Im of 0 implies that we do have now these factors that are decreasing all the way to 1, which means we have an n factorial, but then we have the negatives, right? These negatives, which means we have negative 1 to the power so we have n, right, to the power n over m plus 1 times, so we have one way of doing, so we have n times Im of 0. So we have Im of n, we've found it to be negative 1 to the n times n factorial over m plus 1 to the power n Im of 0, or Im 0, which is the same as negative 1 to the n factorial over m plus 1 to the power n times the integral from x equals to 0 to x equals to 1 of x to the power n, natural logarithm of 0, logarithm to the power 0, which goes to 1 here, so we have negative 1 n factorial over m plus 1 to the power n times 0, integral from 0 to 1 of xm. So which is same as negative 1, and sorry, there's n here to the power n factorial over m plus 1. You have x to the power n plus 1 over m plus 1, 0, 1. So since we saw that Im n is equals to negative 1 n factorial m plus 1 to the power n, and we have m plus 1 over m plus 1, 0, 1. We clearly see that this is the same as plus 1 minus 0 over m plus 1, which means that we have negative 1 to the power n factorial over m plus 1 to the power n plus 1. I've shown that I of mn being equal to the integral from 0 to 1 of x to the power m, natural logarithm of x to the power n is equals to negative 1 to the power n factorial over m plus 1 to the power n plus 1. So this is important, and we could get an example. Suppose you have an integral from x equals to 0 to 1 of x squared, natural logarithm of x. This is the same as negative 1 to the power n. What is n? Our n is 1. And then n factorial is 1 factorial over m is 2. So we have m plus 1 being equal to 3. And n being 1, n plus 1 is equals to 2. So we have negative 1 over 9. Okay, so this is an important formula to have in mind. But we're going to proceed to see a situation where here the limit above here is not 1. It's a specific constant. So let's go and see that scenario. So we have essentially shown that the integral from x equals to 0 to 1 of x to the m, natural logarithm, that is equals to negative 1 n factorial over m plus 1 over n plus 1. So this is a unique scenario, and that is when the upper limit of the integral is 1. What about if we have an a, right? what is that? What's the answer there? So the first thing we would want to see is we could say let y be equal to x over a, right? Such that dy dx is equals to 1 over a, and that means that dy can be a times dy can be used to substitute for dx. So when x equals to 0, y would be equal to 0. When x equals to a, y would be equal to 1. So since y is equals to xa, our problem 0 to a xm log of x to the n becomes 0 to 1, and x is ay m log n, and then dx becomes a dy. So this becomes 0, 1, a to the m, y to the m log n. So this and that can come out, so we have a n plus 1, 0, 1, a y rather, ym log of y to the n, and using the rules of logarithm, where if log ay is equals to log of a plus log of y, using this, our integral becomes log of a plus log of to the y to the power n. Okay, so with that in mind, our problem has become, and we have y to the m log of a plus log of y to the power n dy. So using binomial expansion, where if we have a plus b to the n, that's the same as expanding from k is equals to 0 to n of nk, a to the k, b to the n minus k. Using this, our integral here becomes, especially focusing on this, becomes a m plus to the power a m plus n, m plus 1, sorry, 1 y m brackets summation from k equals to 0 to n of the binomial constant, and we have, let's swap it so that we have log to the k y times log n minus k a that. So since our problem has gotten us to this I to the m summation k equals to 0 to n and k, and we have log k log n minus k of a dy. What we can do here, we see that summing integration of a sum of individual components is the same as the sum of integration of individual components. So we can always swap the integration and the summation sign. So we have k is equals to 0 to infinity, 0, 1, y, m, and k log k of y log and k of a dy. And here we see that this and this are constant to this integral sign, so we can always bring that out. So we have nk log n minus k of a integral 0 to 1 of y of m log of n minus n log of k, rather log to the k of y. So we already know this from our previous excursion. So this is m as negative 1 to the power k times k factorial over m plus 1 to the power k plus 1. Okay, so with that in mind, our problem becomes m plus to the power a to the power m plus 1 summation from k equals to 0 to n k log n k a times negative 1 to the k factorial over m plus 1 to the power k plus 1, which is interesting. So what that tells us that the integral from 0 to a of x to the power m log n of x dx is equal to a to the m plus 1 summation from k equals to 0 to n of negative 1 to the k n k k factorial times log of to the power n k of a over m plus 1 to the power k plus 1. So this here is our answer. Okay, without much ado, much appreciation for those of you who hung with us until this very last moment. We ask you, if you haven't subscribed to our channel, to please consider subscribing to our channel. Until next time, have a good one.